Gauss cyclotomic formulas have multiple representations as x squared minus p times y squared when p is a prime of the form 4k plus 1. We can see here how the coefficients of the polynomials involve Lucas and Fibonacci numbers, providing elegant symmetries. Gauss cyclotomic formula for fifth power have L sub 2m and L sub 2m plus 1 as coefficients in the first polynomial and f sub 2m and f sub 2m plus 1 as coefficients in the second polynomial. Proving this general formula for power 5 isn't overly challenging. By expanding the squares, we arrive at a fourth degree homogeneous polynomial, where it becomes evident that x, y, and z must all equal 4. This can be proved through the application of well-known identities. The initial identity seamlessly aligns with x, particularly evident when w is replaced by 2m. Thus, x equals 4. To establish the validity of y equals 4, we must initially employ the second and third identities. Through little manipulation, these identities lead us to the first identity, where w equals 2m, thus equivalent to 4. To demonstrate z equals 4, we must leverage the fourth identity. Following substitution and regrouping, this identity converges once more to the first identity with w equals 2m. As a result, z is confirmed to be 4. With x, y, and z all proven to equal 4, this completes the demonstration. Unlike case p equals 5, where we use Lucas and Fibonacci numbers, for primes bigger than 5, we must use Lucas and Fibonacci's polynomials instead. These polynomials naturally extend the concepts of their numerical counterparts. Below, you can see the difference between Lucas and Fibonacci numbers with Lucas and Fibonacci polynomials. Those are the first polynomials for L sub 2m, L sub 2m plus 1, f sub 2m, and f sub 2m plus 1. For Gauss cyclotomic formula for power 13, those are the coefficients for each polynomial. Notice the tight symmetries of the coefficients. When examining Gauss cyclotomic formula of 17th degree, we continue to observe the noted symmetries. However, it's worth noting that the coefficients for the first polynomial incorporate a factor of 1/2. Later, we'll see that this adjustment corresponds to an identity, probably already discovered, for other primes 4k plus 1 with representation as x squared plus 1. Here we have the coefficients for Gauss cyclotomic formula for power 29 and Gauss cyclotomic formula for power 37. Here we also have the 1/2 factor applied in the first polynomial. Keep in mind that 37 is represented as 6 squared plus 1. However, when attempting to derive the coefficients for Gauss cyclotomic formula for power 41, it becomes evident that they could no longer be determined through a straightforward combination of Lucas and Fibonacci polynomials. The good news is that it's still possible to find symmetric formulas involving values taken from the solution of the Pell equation 41x squared minus y squared equals 40. Remarkably, all preceding cases can be reformulated in relation to solutions of the Pell equation. Let's examine the case for the fifth power. The first solutions to the Pell equation 5 times x squared minus y squared equals 4 are displayed below. Those values of x and y exhibit a linear recurrence. We define now x sub m, y sub m, w sub m, and z sub m. Representations stemming from solutions to the Pell equation also reveal exact symmetrical patterns within polynomial coefficients. While this connection may initially seem shoehorned, these symmetrical properties persist when p increases in magnitude. Next, we will illustrate how the coefficients derived from the Pell equation extend to primes of the form 4k plus 1. We will also visualize the symmetrical structure of these coefficients within polynomials. You may pause at any time, as the slides will only be displayed for a few seconds. Now we'll display in a table a summary of the cases analyzed. So a question arises: why did the solutions to the corresponding Pell equation work for all cases, but only succeeded in some cases when using Lucas and Fibonacci polynomials? Well, the explanation arises from a broader application of the well-known identity used in demonstrating Gauss cyclotomic formula for the fifth power. This is the well-known identity utilized to show the case for the fifth power, and below we show that it can be generalized for certain other values, though not universally. These identities were most likely discovered before. The blue-colored identity revolving around n squared plus 2 squared proves effective for powers 5, 13, 29, and 53, while the gray-colored identity centered on n squared plus 1 applies to 17 and 37. However, neither of these identities holds true for other primes of the form 4k plus 1, such as 41, 61, 73, 89, and 97. This elucidates why certain prime numbers, which are sum of two squares, resist representation as differences of squared Lucas and Fibonacci polynomials. By the way, these identities give solutions to the Pell equation for some of the values that are n squared plus 4 or n squared plus 1. Finally, the light blue colored identity says that Gauss cyclotomic formula coefficients for power 53 could be expressed in terms of Lucas and Fibonacci polynomials. And given that we already found the form with the solutions to its Pell equation, we can also find the form using Lucas and Fibonacci polynomials. In conclusion, Gauss cyclotomic formulas have multiple representations as x squared minus p times y squared for all primes of the form 4k plus 1. Initially, we illustrated how the coefficients of the polynomials involve Lucas and Fibonacci polynomials when p is either of the form m squared plus 1 or m squared plus 2 squared, manifesting elegant symmetries. Subsequently, we presented a method for finding those multiple representations as x squared minus p times y squared for all cases, applying the solutions to the Pell equation p times u squared minus v squared equals p minus 1. These representations, too, reveal remarkable symmetrical patterns, enriching our understanding of Gauss cyclotomic formulas. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. If you haven't already, consider subscribing to my channel for more elementary number theory content. Stay tuned for future videos by hitting that notification bell so you never miss out. Your support means a lot.